Hello. In previous videos, I have explained to you the topic of linear regression, and in today's video I will start with another topic of data science called nonlinear regression or polynomial regression. And I will start by explaining the idea and the theory behind the nonlinear regression modeling. So within the explanation of linear regression, we saw that if we have, for instance, two variables like height and weight, and we found there are certain level of correlation between these two variables, such that they growing together or shrinking together, then we can build a linear model or find the linear function that can express the relationship between these two variables, and we can use this regression model in order to predict a value of one variable knowing the value of another variable. So for instance, if we have a set of observations like what we have here, and we use this set of observations called also the training data in order to build our linear regression model, then we can use this function, this linear function, in order to identify the value of the weight, for instance, for a new unseen observation if we only have the height of this observation. So this is the way we make use of the linear regression model. So in today's video, I will explain some similar topic in data science called the nonlinear or polynomial regression model. And actually the motivation behind the nonlinear regression is that in real life the relationship between variables are not always linear. So for instance, if you are doing some physical training, you will notice that the average number of your heartbeats is increasing in a very considerable way in the first 5 minutes of your exercise. After the 5th minute of your training or of your physical exercise, your average number of heartbeats will start to decrease as long as you continue doing your exercise. So this is one example of the nonlinear relationship between two variables in real life. As another example of nonlinearity between two variables is the concentration of testosterone hormone in a man's body. So it is scientifically well known that the concentration of testosterone hormone in a man's body is increasing from the age of 25 to the age of 35, expressing this domain of the function. And at the age of 35, the level of testosterone starts to decrease monotonically as the man getting older. So this is another example of nonlinearity between two variables. So before I jump to the theory of nonlinear regression, I want to explain briefly what do we mean by nonlinearity of a function. Actually, we call a function as a nonlinear or polynomial function if this function has more than one direction. So for instance, in the linear modeling or in the linear function, we call it linear because it has a single direction over all of its domain. So here this green line, when we read it from left to right, we notice that it has only one direction. So this is a linear function, or we can call it a polynomial function of the first degree because it has only a single direction. If we take another example of this function, we call this function a nonlinear function of the second degree, of the second polynomial degree because it has two directions over its domain. So starting from this point, the function starts to increase up to this top value. Afterwards, the function starts to decrease. So we called it a nonlinear function of the second degree. Another example here is also a nonlinear function of the third degree because the function has three directions. It starts to decrease and increase and once again decrease. So the function has three directions, and therefore we call it a nonlinear function of the third polynomial degree. And the number of degree of directions of a nonlinear function reflects always its polynomial degree, as I have mentioned before. So here, for instance, the linear function is a polynomial function of the first degree of degree equal 1. And you will notice that the mathematical definition of a linear function contains a single term of variable x, and also the power of x equals to 1. So this is how we can know that we are talking about a linear function, because we don't have terms of x variable higher than 1. If we move to the mathematical definition of the nonlinear function of the second degree, second polynomial degree, we'll notice that we add another term of x to the power of 2, and this means that this function is a nonlinear function of the second degree, of the second polynomial degree. The same case with the polynomial function of the third degree. We'll notice that it contains always the x term to the power of 3, so we have x cubed, and this means that we are talking about a nonlinear function of the third polynomial degree. So this is how you can know the polynomial degree of a function, either visually if you visualize it, or if you read its mathematical definition. Now we move to the theory behind nonlinear regression topic, and in this video I will use the same methodology I have explained before in the linear regression topic, which is called the least square approach. And within this approach we try to find a nonlinear function that minimizes the summation of distances between itself and the true values expressed by our target variable y in this case. So we try to find a nonlinear function that minimizes the distances here explained in these vertical green lines you see. So mathematically we have an error function or a cost function called E of w, where w represents the vector of coefficients that expresses this nonlinear hypothesis or this nonlinear function, and we define it the same way we define it in the linear regression, which is equal to the summation of differences between the vector of true values y super I, which are represented by these blue dots in this figure, and the hypothesis itself, which represents the curve or the nonlinear function we are trying to find. And we compute the square of these differences, such that we can regularize between positive and negative differences, and we compute the average of all of these differences. So this is the function we are trying to solve in order to find the set of coefficients w that best fits this non-linear regression model. So within the linear regression, our hypothesis function f of x super I and w were represented by two terms, W0, the intercept coefficient, plus W1 multiplied by our predictor X super I. Within the nonlinear regression approach, this hypothesis function is somehow expanded to include terms of higher polynomial degrees, such as we can have x2 multiplied by x super I square, x3 multiplied by w3 multiplied by x super I cube, and so on, up to the level or the degree of polynomial we are searching for. So this is a flexible definition of the hypothesis function of nonlinear regression that you can use as many level of polynomial as you wish in order to fit your data. And we can also express this regression equation into a more compact form in using a sigma notation, such that we have a WP multiplied by x super I to the power of b, where p is moving from 0 to capital B, where capital B is the level or the degree of polynomial of our nonlinear regression function. So our goal is to find the vector of coefficients W that minimizes our cost function or our error function. And as I have mentioned in the previous videos, we follow 3 steps in order to minimize the error function. The first step is to compute the derivative of the cost function with respect to each coefficient into the W vector of coefficients. Second, we set the generated derivatives to 0, and we obtained afterwards a set or a system of equations that we can solve mathematically using either a closed form approach or using an approximation algorithm like the gradient descent algorithm. So we start to compute the W0, the first coefficient, by computing the derivative of the cost function with regard to W0. So this will equal to the 1 by n multiplied by the summation of the derivative of the expression y super I minus w naught plus sigma wp x super I to the power of b all squared. We will try to compute the derivative of this term with respect to W0. We start to expand the expression inside these square brackets. So we will get w super I square minus 2 w naught y super I minus 2 y super I multiplied by the sigma of wp x super I to the power of b plus w naught square plus 2 w naught multiplied by sigma wp x super I to the power of b plus sigma wp x super I to the power of 2p. After having this expression, we will try to compute the derivative of this function term by term. So when we're differentiating this term with respect to W0, the first term will be deleted. The second term will equal to minus 2 y super I here. The third term will be deleted. This term will be equal to plus 2w0, which is here. This term will equal to plus 2 sigma wp x super I to the power of b, which is here. And this term will be deleted. Again, we will try to simplify the equation by sending minus 2 outside the sigma. So it will be minus 2 divided by n multiplied by the sigma of y super I minus w0 plus the sigma of wp x super I to the power of b. So now we obtain the first derivative corresponded to the first coefficient term W0, which is equal to this term. So if you repeat again the differentiation process in order to compute the derivative of the cost function with regard to the second coefficient W1, you will end up to the same result as the output of the derivative of W0, but multiplied by x super I. And if you computed with regard to the third coefficient W2, you will find the same output but multiplied by x super I square. And if you repeat the process for any polynomial degree, you will always reach up to the same result of the first derivative of corresponding to W0, but always multiplied by x super I to the power of b, where p reflects the polynomial degree of the term you are trying to find its corresponding coefficient w. So after computing this derivative, or this set of derivatives corresponding to our vector of coefficients, we will try next video to compute or to find the list of coefficients w using either a closed form approach or a gradient descent algorithm. Thank you for your time.